So I'm going to talk now about intergalactic filaments. It's highly connected to many subjects that we've heard about during the week. Thanks to Nir and Han this morning, a lot of the introduction has been already made, but I will repeat some of the small points. I work with Avishai Dekel in the Hebrew University in Jerusalem, and with a lot of other people on this subject. I will show you a selection of some points that we have discovered about those filaments, and I will first try to explain what they are and why studying them is important. So at first, you all know this picture from the Millennium simulation, where we see a lot of filaments. This is what I call intercluster filaments. Intercluster because they mainly connect nodes that correspond to dark matter halos of clusters, of galaxy clusters. But in fact, it's a multi-scale structure. So there are big and small filaments, and there may be a continuum of scales between those things. The same would apply to walls and to voids and to halos. What I call intergalactic filaments connect filaments. So galaxies can be embedded in intercluster filaments, not, of course, in intergalactic filaments. The IGFs, as I call them, are not only a skeleton for the system of all galaxies, making them a rigid network. They are also pipelines, which means that, in fact, dark matter and gas flows along them. So as you can see, where is this? Yeah. As you can see here, it flows in one direction when you are closer to one halo, and in the other direction, closer to the other halo. Here exists a saddle point. So there's also a specific topology associated with that, which makes them detectable in simulations. They often, I put this here, as Nir said very rapidly this morning, they mostly arrive in a coplanar fashion to the halos, and especially to the galaxy, but even at the Radial radius. And then their number is most often 3. That's another problem, but that's also an interesting thing to study. A few facts about them. So as I said, they are part of the cosmic web. They are the one-dimension elements, as we could think of, if the halos are the zero-dimension elements. There are, in fact, at the intersection of 2D elements that are sheets that themselves separate voids, the 3D elements. The typical length, say at redshift 2, of an IGF is 5 times the virial radius of a typical halo connected to it, and has in total almost the same mass as these halos, the halos that are at the two ends. They are always out of equilibrium. They are not virialized, so it would be difficult to imagine a virial system in this cylindrical geometry for those flows, because they live also, that there is a strong axial gradient that they live in. And transient because we think of them as solid rods connecting the halos. But in fact, if you follow in a Lagrangian fashion a particle, it will be attracted, for example, from a void by the filament, go into it, flow into it, and finally end up in the halo. That also means that it's not easy to produce a zoom-in simulation for filaments, especially. For halos, we know that if the particles have fell into them, we can trace back a Lagrangian patch, follow it, and we will get the halo we want. It's not true for a filament, because at some point the particle will be in and then out. So we have to combine geometrical or other physical quantities into the criteria for zooming in. And their core is what we can call the cold stream. So after it has penetrated the halo, after the virial radius, the gas that has cooled down close to the axis of the IGF will either be destroyed in the halo or feed directly the galaxy. So why should we study them? First, as Nir said, because it's cool. And second, if we study halos, we should study every other object at any dimensions. So they are the natural structural extensions of halos, and in fact, they are the things that give the first anisotropy to halos. Then, because if we want to study problems like Nir and Han study, we need initial conditions. And those can only be given by simulating or having toy models for filaments above the virial radius. And perhaps they may also fragment before entering the halo, which would mean that there would be no cold stream in the halo. They could be destroyed by many effects inside the CGM, but they could also be destroyed before entering the halo. And finally, up to the redshift 1.5 or even 1, they are the major contributors of mass and angular momentum acquisition for the halo and for the galaxy. So we have to understand these. When I say these are major contributors, you have heard Avishai several times comment on things here, saying, and what about accretion? Because we have heard a lot about feedback. Sometimes the feedback is too strong, sometimes it's not enough. We want to turn this button. But we shouldn't forget that the accretion is also a button that we can turn, that we can moderate. And since it comes mainly in the form of filaments, this has a special physics attached to it. And this moderation is a consequence of the gas physics I want to study. Most of you know this picture about the filaments. So in mass of the halo and redshift in this plane, we know that filaments must not be destroyed by a shock at high redshift for high masses, and that they represent up to 70% of the mass acquisition of the halo. So I'll skip on this one. So we have a lot of processes happening in halos. Processes that evacuate energy, that accumulates energy, same for the mass. And the filamentary accretion, we don't know yet what happens after the entry, and we have to know what happens before to complete this whole set of physics to understand the galaxy evolution. A few guidelines for this research. A lot of things can happen. First, we know that we see them in simulations, but we don't really see them in observations. Well, thanks to Chris Marlin, maybe we will see them better in the near future. We want to know under what conditions they can be found. How could we see them? In what environment? At what redshift should they exist still? Up to what redshift? What would destroy them? So gas instabilities, as Nir has, and Han have said this morning. Other dispersion mechanisms, as I have studied during my PhD thesis. Or other kind of fragmentation even above the virial radius, like Jonathan Freundlich, Han Ong, and other people have tried to study very theoretically. What would happen to the remnant material? If you produce fragments, then it's not a cold stream, but then it means that the galaxy should get intermittently very cold and very dense material. So it would change the physics of the galaxy and include clumps into it. And again, even if we identify some instabilities that can happen, are there mechanisms that would protect the filament from those instabilities? For example, if the sheets connected to the filament are giving enough mass and enough pressure to survive some instabilities, it can prevent the destruction. Same if the rotation, the intrinsic rotation of the filament helps, then we have to know about it. And we will see where it can come from, this vorticity. So first, I will show you results from a first simulation run with Ramses. So thanks to Cameron, now everybody knows what the AMR, the Adaptive Mesh Refinement is. Ramses is that kind of code. And I ran a cosmological simulation and then a zoom-in simulation on a specific halo, which is a little bit more than 10 to the 11 solar masses at redshift 2. And then I identified a filament and I cut it. So here it's a transverse cut of the filament. So what you see here, the first plot, it's the density field. You first see that it's strongly anisotropic. So the smallest circle is at 30 kiloparsecs. The second one is at 90, and so on. So just to give you a scale. You see that there's a strong anisotropy. It looks like a halo with filaments connected to it, but no, those are sheets, in fact, connected to it. And here it's a companion filament. In temperature, you can identify a shock all around it. And here in the baryonic fraction, you can see that it's here in the shocked medium lower than the cosmic value, and in the center, much higher. So it resembles a lot a halo. What we will see now is that there is a specific pattern for the velocity inside it. I will skip those profiles and go directly here. First, we can see from the divergence, so which is a local measure that defines here, of course, the shocks, but also inside it, a region which is divergent and then convergent again, that it's accelerated and cooling, like in the halos. If we have a look at the vorticity itself, again, a local measurement, we mostly identify the shear, but it also traces main vortices that Clotilde L'Aigle had found in 2015 in intercluster filaments. And here we can see it's the same kind of behavior. And since the two sheets are not perfectly aligned, there should be, in the middle, an average rotation. And finally here, I plotted the baroclinic term. I don't know if everybody knows what it is. It's defined like this. It's the cross product of the density gradient and the pressure gradient. When they are not aligned, vorticity should be produced. So of course, even if this term, here you can see in orders of magnitude, it goes from 8 in black to 17 in red. So even if this term is very, very high, it doesn't mean that there is a lot of rotation at the end, because first here it would be the integrated story of the vorticity derivative. And second, my resolution is not sufficient to prevent the numerical dissipation, numerical viscosity. Then I wanted to show you that, so I won't enter into the detail of the cooling, the effective cooling time, which measures a kind of thermal instability time. And it's the product of the cooling time that we know, and another quantity depending on the cooling function. When we combine those two pictures, we understand that here, where the cooling time is short enough and the second term big enough, the medium should become multiphase. Again, because of the limited resolution, it won't happen, but it should. So in fact, the filaments, even before entering the halo, should be turbulent and highly turbulent and multiphase. Now let's see a radial profile. It's not easy to do because you have to define a center, and as you know, it's the same for the halos. Finding a good center for example, the gravity is maybe not a good center for the rotation and so on. But once we have one center, still in the transverse plane, we can plot radial profiles of the pressure in yellow, the centrifugal force, which uses the average rotation. In dashed, it's not the average, it's the square root of the average of the square. Well, in fact, it's equivalent to a turbulent term. And you can see that the whole pressure, the total pressure applied, increases, mostly here close to the shock, thanks to the pressure, the thermal pressure. Then there's a loss, but here in the center, when it's cold, it's increasing because of the average rotation, and finally very close to the center, thanks to the turbulence. So that may be a good way of sustaining a core. So I'll pass on that. Now you have understood the many analogies between halos and filaments in another dimension. And I'll go directly to the second simulation of a higher resolution, and this time centered on the cold component of the filament. Nir has shown this picture this morning. This is the density, this is the temperature. It's badly resolved in the center, close to the galaxy, but here it's better resolved. You can see here a periodic pattern in it. We know now that it's not the Kelvin-Helmholtz instability, unfortunately, but because there's no shear, as we will see. And I won't talk about this pattern right now, but preferably I will study the evolution with what I call the altitude, well, the distance to the center of the galaxy. Here it's the linear mass. You see that outside are there, it's almost constant. This is the total, in black the dark matter, in blue it's the cold gas. It's everywhere called low entropy gas because it was easier to separate by entropy in the data. And here, those are the mass fractions. So here it's the baryonic fraction, and you see that it's very high in the cold filament, that it's mainly carried by the low entropy, well, the cold gas, while in the surrounding hot medium, it's very close to the cosmic value. And then everything drastically changes close to the virial radius, because mainly of the mixing of the hot phase with the halo gas, and then the cold stream is in direct contact to the conditions of the halo. And something else happens. Here you can see that there are strong peaks that we recover here in mass. It corresponds to a fragmentation inside the CGM and must correspond to the things that NIR studies. But here, outside the virial radius, you can see that the infall velocities are very close for the high entropy and the low entropy gas. That means there's almost no shear. So in fact, this hot sheath almost protects and is in pressure equilibrium, protects the cold stream as long as it has not entered the CGM. Here, rapidly, it's the average rotation. You can see that here it's almost constant with a small fluctuation, and it falls down inside the halo. So this average rotation may protect the cold core, but not after it has entered in contact directly with the hot halo. And here it's the equivalent, but for the turbulent term. And it's the same story. It falls down after the entry in the halo. So here are my conclusions. IGF are important. They are not passive. They look like halos. They must be turbulent and multi-phase, and it must have a lot of consequences on the mixing with the CGM. And finally, the inner turbulence and vorticity may help sustain these cores. And these are the further questions I can leave.
Questions?
Really cool work. Did you do any kind of conversion study to see how the properties of the filament changed as you increased resolution on it?
Yeah, in a way, yeah. Using several simulations, but with very different resolutions. In fact, the lower the resolution, well, I should say the poorer, because sometimes we think, yeah, the poorer the resolution, the less cooling we have inside the filament. So if the resolution is not sufficient, we will have only tepid filaments, and the hot and the cold phase will be mixed. It's very close to what you found close to the halos, close to the galaxies inside the halos.
Another question?
Stability might not be important, and is that the thermal stability?
Outside the halo.
Outside halo.
Because there would be no direct shear between the cold and the hot phase.
How about the thermal instability?
The thermal instability, that was the meaning of this effective cooling time. It should occur. So I shouldn't say thermal instability. A thermal instability, to compute it, you need an equilibrium situation. Here, in fact, even with an average cooling of the whole medium, some parts may cool even faster than the average, and that's what is used to calculate this time. And yeah, it should form a multi-phase medium.
Hi. So just a brief comment about the Kelvin-Helmholtz instability outside the halo. I agree that there probably isn't any shear, so the Kelvin-Helmholtz that I talked about probably isn't operating outside the halo. But the instability that Han talked about, which has to do with a self-gravitating cylinder with a density discontinuity, does not require any shear to operate. It just requires a cylindrical geometry of a self-gravitating cylinder with a density jump. So that might very well be what you're seeing.
Yeah, that's possible. In the first simulation I showed you, in fact, I have found some big clumps of the size of a few 10 to the 8 solar masses, baryon rich. I still don't know what it is because it was a poor resolution, but that may be the result of what Han is studying, yes.
We're getting into our break time, so I think we'll cut it off so we have a little respite, and we'll be back here at 3:50, but let's thank our speaker once again.
Thank you.
And just one more note, there's still one container somebody left at Brant Robertson's place for the potluck, so if that's yours, talk to Brendan.